Hi everyone, let's tackle another of these classic calculus problems. So in this problem, we're starting with a piece of cardboard with some sort of set dimensions. We have 50 inches by 25 inches, and we are supposed to cut out little squares from each corner. And once we've done that, we fold up these remaining edges. That looks a little too big. And that's what creates the box. So the dashed lines here are the folds. The corners are gone. If you fold up, then this becomes the height of your box. And this is the length of your box. And this is the width of your box, or vice versa on the length and width. It doesn't really matter, but you want to imagine that fold happening and the height sticking up out of this page. So we are supposed to express the volume of a box as a function of the length x of the cutout. So what I'm saying here is that we're cutting out x inches from each side of the box. So that little square that I've shaded in is x by x. Okay, so volume, V is already defined for me. Volume of a box is length times width times height. And I do want you to know that one. So if you don't already, make sure you memorize it. It's a fairly simple one. I'd like you to know all of the prisms. So anything where you take a two-dimensional shape and you just stretch it out, and that gives you a volume. All right, so we need to get all of this in terms of our single variable x. So I don't need a perimeter formula or anything like that, but I do need to really look carefully at this. The first thing I'm noticing is if I fold, so let's see, for example, I fold this up so that it's sticking out of the page, the height sticking out of the page will be x. So the height of this, so I'm going to make all this as a function of x. The height of this is actually the easiest part, I think. It will be x high. It's easy once you've got the visual. If you're not picturing this right, that can seem a little tricky. If I want the length of the box, it's not going to be 50 inches. That's the length of the cardboard. It's going to be what's left after I cut this little box out of each side, this little square out of each side. So if those are both gone, what's left here in the middle is that 50-inch length of the cardboard minus 2 of those x's. So if I want to call that length, 50 minus 2x is my length. Similarly, for the width, if I take an x out of each side, so I take an x out of each side of the cardboard, what's left in the middle is a 25 minus 2x. So the width is 25 minus 2x. And this problem just asked for a setup, so I'm actually done. I don't need you to multiply that out. I don't think it makes anything any easier for our purposes. Maybe in calculus, the next step would be a little easier with it multiplied out, but I don't care here. I will say, we are absolutely capable right now of going and typing that into Desmos and finding the maximum, and we'll do that at certain points during the quarter. But for now, the only other thing that I want for this problem is to state the domain of this function. We need to recognize that this is an application. This is a word problem, so I'm not just saying physical domain. This is cubic, so if I was just saying like the domain of the function without thinking about cardboard or boxes, it would be all real numbers. You can plug anything you want into a cubic, but there are things that are practical and impractical in the context of this problem, and that's what this is asking you for. So it's asking you for the biggest and smallest x that make any sort of sense. This is not asking you to pick out the x that will give you the biggest box, which is what we typically would be looking for in the end of this problem. It's saying what x's give you a possible box. So if I think about smallest possible x, I think 0 is a fair choice here, and I actually don't care if you include or exclude the 0. So if you give that a round or a square bracket, if my open math is really picking on you and driving you nuts, let me know. But typically for my purposes, I'm okay either way. I think there's a strong argument for both. One, if we include 0, what we're saying is that it does have a practical meaning. If you don't cut anything out, you still have a piece of cardboard. I can explain what that means. It's a bad choice. You don't have a box, but you do have a piece of cardboard, and I understand how to visualize that. The argument against including it is also kind of in what I just said. It's that you don't actually have a box. So if you don't make x bigger than 0, you're not getting the box at all. I typically will include it in calculus because it makes the last little bit of maximizing one of these things just slightly easier if you include it, and it's not going to get you in trouble either way as long as you're aware that there's no box there. That's just a flat piece of cardboard. On the bigger end, sometimes it takes people a little while to work their way up to this, but if we start thinking about this, if we cut out, let's say, x equals 2 inches from each side, we're going to get a box that is, let's see, we can look at our things. So we're cutting out 4 inches total, so we get a box that's 46 by 21 by 2. If we jump up to x equals 5, you do not have to do all these calculations, but I just want you to kind of see my thinking. I end up with a box that is 40 by 25, 15 by 5. This is all great. If I jump up to x equals 10, am I still good? I think I'm still good. I get a box that is 30 by 5 by 10. Okay, what if I jump up to x equals 20? If I jump up to x equals 20, I get a box that's 10 by negative 15 by 20. This is where I have a problem. I don't want to have a negative dimension of my box. So what we're looking for is where's the cutoff, and the deal is that the first one to cause you trouble is the 25 minus 2x. As soon as we hit 12.5, it causes that factor to become 0. So what you're getting there is if x equals 12.5, you have fully cut out and not left anything in between. If you can kind of see that, your cutout is now all of this. You've cut out 12.5 inches from that side, and you've cut out, this is probably, it looks a little bigger than 12.5 inches from that side, and you're just left with this little piece of cardboard in the middle. So again, it's not a box, but it's the extreme of what you can actually make sense of in a real world context. If you go anywhere beyond that, it's impossible. You can't cut out more than 12.5 inches from each side of a 25-inch piece of cardboard. So the domain of this is everything from 0 to 12.5. The maximum will probably lie somewhere in the middle, but those are all the possible situations that make any kind of sense in this problem. All right, thanks for watching.